Thank you. I will say it's a hard talk to follow up on for Tiff, but I'll try my best. And also thank you all for sticking around quite late. So this is work done with Kshitij, Tarun, Theo, who's over here, and Alex Evans on kind of just like a nice conceptual framework for reasoning about constant function market makers. I'll get into what constant function market makers mean. I suspect most people here kind of know what it is. I don't know if everybody does, but we'll get into it. Okay, so quickly, everybody knows, I suspect, what automated market makers are, but if you don't, it's rather simple. We take a contract. So a contract here is, for example, a computer program with holds n essence. And anybody can come up with this contract and propose a trade. A trade here is going to be denoted as a vector with n coordinates. For example, denoting how much I'm willing to tender or receive from this contract. So, for example, delta 1 is positive, I'm willing to tender some amount to the contract, and delta 2 is willing to receive some amount of and then the contract simply decides based on its current state, which I will specify what it is in a second, to accept or reject that trade. If the trade is accepted, then all values get netted out. So everything I promised to tender the contract gets added to contract reserves, which are another n non-negative n vector, and everything that I propose to receive gets paid. And finally, kind of as expected, the reserves, which are the values that this contract holds and from which it pays out, are updated in the standard. Everything is just okay. So constant function market makers are possibly the simplest, non-trivial automated market maker you can think of. In this case, there is some rule you want to call a trading function. That is simply a function which maps the non-negative real n vectors to a real number. In our case, this will be a concave non-decreasing function, although we can relax assumptions considerably. And here, the rule is that a trade is accepted only if the reserves, if the trade were to be accepted, are at least as large as some constant k, right? So that's fairly simple. It essentially asks, look, if I were to set this trade and I'm netting out my reserves, is this function at least as large as sk? And the classic standard version of this is Uniswap. So Uniswap is the simplest version, which is, sorry, you can see it there, but it simply says, okay, give me two vectors, those trades, two tokens. I will take the product of them, and the reserves after we make the trade their product had better be at least as large as the product of reserves prior to the trade. So this particular constant. Okay. So why do we care about these things? I mean, fundamentally, it's kind of a silly rule, right? So at a high level, there are a bunch of on-chain markets, decentralized exchanges. Actually, if you pull up your favorite search engine and take a peek at some of those exchanges, you'll probably get a list of 50 or 100 or so. I can list them out, maybe some of these names sound familiar, maybe they don't. There's Uniswap, there's Balancer, there's Curve, there's Uniswap v3, there's Pendle, and so on and so forth. The one important thing is, which is quite unexpected, I think, to a lot of people in finance and economics that are not familiar with blockchain concepts, is that essentially all of these things are not order books. They're not kind of the standard traditional financial instruments that one uses for exchange. They're organized as these constant function market makers. And that might seem, again, a bit silly, like, okay, who cares about that? Crypto market exists out there. But in reality, these things average about $1 trillion in volume per year. So they're, at least just for that reason, they're kind of worthy of study. Okay, so why this paper, right? Look, these things have existed for 6 or so years. Certainly, if there's $1 trillion looking through these things, people have studied them deeply, have some cool results. And my argument will be that actually many of the results that we seem to focus on are actually what I'll call an algebraic functional. They rely a lot on the definition of this trading function. And my argument for this particular paper will be that, in fact, fundamentally, constant function market makers are geometric objects. There's one thing I hope you come out of this talk is that is the simplest possible definition of what we can come up with that satisfies all of the axioms of this. And in fact, that geometric object has extremely intuitive properties for how it behaves. Okay, so the natural next question of a good framework is, cool, given that you've set this thing up as a geometric object, and you actually derive anything useful, like you derive the original results and maybe some extensions. And the answer is, well, hopefully, yes. Okay, so with that, I guess I have to introduce a little bit of convex geometry, and this will involve totally overriding the previous definition I gave you of constant function market makers, and then rebuilding it using purely geometric. Okay, so a constant function market maker is now going to be defined by a set S. That set is going to be a set of points which are non-negative n vectors. And it has to satisfy two properties. First, it has to be non-empty, closed, and convex. Non-empty essentially is a non-triviality assumption. Closed is a technical assumption because, like, what the hell is an open set versus closed set even mean in real life? I don't know. And then convex will have one important implication, which says the more you buy of an asset, it cannot get cheaper. That's the only direct implication of convexity. The last one, which is actually also, funnily enough, technical condition, and I'll explain why in a second, is the following. If a point, in other words, if some point R lies in the set S, then if you have another vector, which is element-wise at least as large as R, let's call it R prime, that R prime must also lie in the set S. If you think about it in 2 dimensions, and I'll show an example in a second, it's roughly saying you have a set and it's every point above and to the right of that set is always filled in. Of course, you can take this upward closure of any set. So in sense 2 is kind of a little bit of a condition that we're making that is kind of without loss of generality. Okay, so that's it. So let's present. This was the previous trading function that I just showed you. So this is Uniswap V2, where it shows in AB1, and here's the set. And it's pretty easy to see that it satisfies all the desired properties, right? It is simply a set of reserves such that R1 times R2 is greater than set. Not just greater than V1, but V1. So certainly this thing is not empty. I mean, 1 is in the set. You can also see all the points in the set. It's certainly nice. Every point above to the right of any other is certainly included in the set. That's easy to see because R1 and R2 are put on a function. This set is convex. Again, easy to see from just like looking at it, but you actually want to sit down. That's all paper. And last but not least, this thing is closed. That's because R1 is R2 is the instruction. So, okay. So, I've explained to you what we've now redefined the CFMM as, but what are its mechanics, right? How do we get back to kind of the original CFMM, right? The CFMM has these exception trades. What does that mean? So, one sense to think about the set is it's going to be the set of states available to the CFMM. In other words, the set of reserves which are consistent with the CFMM's kind of behavior. So if the CFMM starts at some reserves R, any trader can come and propose a trade delta, which move those reserves to R plus delta, so long as those new reserves R plus delta are also in the set. And that's what we call a valid trade. So we call it a valid trade if whenever you add it to the current reserves, you also still end up in the set. Another kind of intuitive way to think about it is, look, you're able to move to any set of new reserves, which also lies in the set, by just paying the difference between the previous reserves and the new. Okay, and this of course includes the original definition, right? All we say is, cool, you take it's a constant function market maker, simply define the set as a superlocation of the whole set of your constant function. And you can see this master. Okay, so why do all this work, right? I mean, look, we just kind of said a thing. This clearly contains the previous definition of constant function market makers, and all we've done is just kind of wrap it up in some nice, silly language where we call it set. So I'm going to give you actually a set of direct implications that come from just being able to write this thing down and noting that it's a convex set with its properties. And these are very not obvious. So the first is that reachable sets are closed under essentially 4 very natural operations. When I say a reachable set, I mean a set that satisfies the 2 properties they give. Number 1 is that they're closed under Minkowski addition. Minkowski addition is a set by sum, which takes, if you sum 2 sets, you take 1 point from each set, add it together to receive 1 point in the resulting set. It's easy to see that this is, I'm going to come back by writing the definition, non-empty certainly, and upward closed. And you can see there's adding the points together. If there's a closedness, it's a little bit more annoying, and so I'll leave that. Or you can do positive scaling. Positive scaling certainly maintains all the definitions directly. You can do set intersection, like arbitrary set intersection, so long as you can guarantee that the resulting set is empty. And you can do non-negative matrix multiplication. So if you pointwise multiply every element in the set by a non-negative matrix, you get another reachable set. And here you see one specific example. So if you're familiar with Uniswap V3, on the left, or I guess on the right in this case, are 2 sets which correspond to Uniswap V3 ticks, and then on the right you have obviously another set which satisfies exactly the conditions I mentioned before, that is itself kind of corresponding to a Uniswap V3. So if you're familiar with that, that's great. If not, just know that this is an example of showing them in cascadation kind of preserve the properties of this. Okay, so now let's say, I've mentioned that like, cool, this is a generalization of, canonical version of the constant function market maker, which is a trading function. Is it equivalent? And the answer is yes. We can construct from any set S a trading function in this kind of silly way. And the interpretation is rather simple. What we're going to say is, okay, the trading function is defined as the following. You give me some reserves, and I'll find this largest scaling I can, such that R over lambda supplies this. The picture is rather silly. Certainly, if R is in the set, right, then lambda L will be at least, because we can always scale it down. On the other hand, if lambda is not in the set, then we must scale it back up, right? We must push it towards kind of the boundary of the set. And so, okay, why this definition? There's certainly many definitions which would satisfy the, nice property that it returns the constant function market maker. So, obviously, as I mentioned before, from the canonical trading function, we can recover the set by exactly the argument I gave. But also an important property is the canonical function is homogeneous, concave, and non-decreasing. And in fact, it is the unique function which recovers the trading set up to scaling. So any function that recovers exactly this trading set is going to be pointwise identical to the canonical trading function up to a scaling constant. So this is actually already known is, right? Kind of silly when you look at the definitions, but this was, as far as I know, not known. Every CMM actually can be turned into this function. And so, of course, we could say, okay, we have the trading set for Uniswap. What is this canonical trading function? And you just write out the conditions to get square root of R1 and R2. Easily seem to be homogeneous if you multiply R1 for 2 by some factor, it pulls out. Concave, this is a way to do, or is it just a geometric mean, and it's not increasing. Because it's not increasing. So this thing is canonical in this. Okay. So funnily enough, the canonical trading function plays second fiddle to what I'll call the liquidity cone, which will be one of the objects I'll introduce in a second. And it has a very similar definition, if you notice. So it's simply the set of reserves and scaling constants, which also lie in the original set. Right. And it's a closure, so I won't too much thinking real analysis. So the picture here is rather simple, and so first things first, it's a cone because if I scale any point in the cone itself, I'll sort of receive another point in the cone. You can see this here actually. If you take any line, it's simply an array, right, applies in the set. And from here, we can actually recover the trading function, right? So it's simply the trading function is exactly the taking values at the cutoff point lambda equals. Okay, so here's the equivalence between 3 objects I've just stated. The liquidity cone, certainly the liquidity cone contains the reachable set. That's pretty easy. It's just simply the set flipped off at 1. And that's easy to see because if you plug in lambda equals 1 up there, R over 1 is an S if and only if R is an S. And cone also gives a canonical trading function, right? As we mentioned before, it is the largest scaling such that R over lambda lies in S. Okay, so I'm going to draw this, someone lovingly called it a treasure map. And I'll add 2 more things to it before we're able to do a few things. Okay. So we have the bijection between the liquidity cone, the reachable set, and the trading function. Okay, and so sometimes we can move across any of these objects. So when you have a cone, the first thing that you should think of in convex analysis, you want to take its dual. There's often beautiful economic interpretations of the dual, and it has some nice properties. So I'm just going to put the definition up there. It's not super essential. But the point is, a closed convex cone has a direct representation. It's called the dual cone. And it's called the dual because if you take the dual, you receive the original. Okay. So in a certain sense, this is simply another representation of the liquidity cone that has a bijection. Okay. Finally, I'm rewriting the definition of the dual cone here with a bit of a change. The point is, if you're familiar with portfolio value function contemplation market making, you should see this term as being kind of the total value of reserves. So if C is interpreted as a price vector of all the tokens, 1 through n, C transpose R tells you how much value the reserves actually have available. And so what does this say? This says, okay, eta must be no larger than the total value of reserves available for every possible state at those prices. So specifically, the portfolio value function tells you exactly what is the value of the CFMM's reserves under no arbitrage. If an external market has prices C for these tokens, what does it correspond to if an arbitrageur comes in and matches those prices together? And that's directly from the dual cone. Okay, so here we now have a full map. We've been eating vegetables for about 15 minutes or so. I think it's time to actually get to some real results. So we can start from any one object and follow arrows, right? Now we've turned kind of a problem that's rather difficult into a mechanical problem. We're figuring out, how to like map one to the other. It's simply just you put the things in and you turn a crank and you get the math out and then you get the exact results out. So let's start with a simple one, which is known. It's the trading function of the portfolio value function. What's the mapping between those? And it actually looks rather interesting. If you're familiar with the Fenchel conjugate, it's exactly the same thing except for the quotient. And backwards, we get this beautiful relationship that says these kind of two objects play the same role. One is over the dual cone, one is over the original cone, right? But in some sense, all we've done is flip labels around, right? So when I say that they're identical objects corresponding to their individual cones, that's exactly what I mean. There's a more symmetric form than was done previously. Another thing that I talked about is we had these operations on the reachable set S. We talked about scaling, we talked about addition, and so on and so forth. So the natural question is, what does those operations over the reachable set correspond to in terms of the portfolio value function? And here I'm going to be very, very careful. It's very important that you don't read this particular slide very casually. The symbols here mean very specific things. So when we write a plus, be very careful to parse the types of the plus which surround. So here's a fun fact. The reachable reserve set corresponding to a portfolio, the sum of portfolio value functions B, is the same as the Minkowski sum of the reachable sets corresponding to the individual functions. The same is true for scaling, and the same is true for non-negative matrix multiplication. Again, this is weird, right? On the left-hand side, we're adding point-wise two functions. On the right-hand side, we're adding convex sets, or reachable sets in this case. So the fancy bullshit mathematical statement is that there exists an operation preserving isomorphism between the reachable sets and these rated functions themselves. Okay, so if there's one thing to kind of keep in mind here, the point of this paper is to essentially draw out all of these equivalences between all of these objects that we generally study. And there's a bunch more. But if there's one thing to keep in mind, it's this particular equivalence. So we can go from any one to any other by just turning it. Okay, so there's many more results. There's simple equivalence to path independence. There's a beautiful set of connections to prediction markets, which actually originally is from Roth, Manisha, and Bo that I highly recommend you go read their paper and then read our like one paragraph version of it. There's many, many more. There's equivalence of routing and plus question market make derivation and such. But yeah, I'll leave you with that. And then if you're really, really curious, here is the preprint. You don't want to wait until the EC papers are done. Cool. Anyways, thank you all.
There can be many shapes of the reverse set. Do you have any idea of which shape is good and which is bad?
No, but Jeff actually does have an idea, and so I would punt that question next. So the answer is you express some beliefs about kind of what your future will be by writing a shape down, but the exact connection is actually not needed. So, and it's actually, many papers actually with many authors from here have exactly that. I think him as well. So